Okay, I would like to remind you, the lightning talks tomorrow. Those of you who have come to me about wanting to do a lightning talk, I will need to see you at lunchtime. So as soon as we go to the lunch break after Igor finishes speaking, I'll remind you. And then I need to find out what you're going to be talking about and set the schedule. And so if you have not yet come to me about a lightning talk idea but would like to, we still have a couple of slots open. So with that, take it away, sir.
Do you hear me? Yeah. Okay, my name is Igor Česi. I work for Ubisoft Paris studio. And if you don't know what Ubisoft does, Ubisoft makes games. So this successfully compiles and runs on Windows, Mac, Linux, and various other POSIX compatible platforms. But have you ever wondered what amount of work would be needed to port D to a non-Windows, non-POSIX platform? How easy or difficult this would be? Or what are the problems which need to be solved? How much time this would involve? If any of these questions you have the answer yes, I might have some useful information for you. But before going into the subject, let me give some context. In Ubisoft, we are a C++ and C# house. We have millions of lines of code. Host development platform is mostly Windows. And we have various targets, all available game consoles, PC on Windows, some Linux, mostly server technology. And our technology per project, which is basically a game, is usually C++ based with considerable compilation times. We are actually not that bad as compared to some other companies we talk to, but we compile like between 1 and 2 million lines of code in 10 to 30 minutes. So iteration speed is one of our never-ending battles, actually. So we have a secret hope that modules in C++ will improve this situation, but yeah, they are late to the party. Well, we have to wait for a long time, it seems. Other thing, memory corruption bugs are super expensive, often hard to reproduce, and even when we reproduce them, it's often too late to figure out what is the cause. So we have some in-house tools like to help debugging, like delayed free allocators, one allocation per page allocators, and different tools like this. But it can still cost like 1 expert week per bug, which is quite expensive actually. There are other advantages in D we are interested in, but they are much harder to justify if you are a C++ house, especially long-term C++ house as we are. So compilation speed and memory corruption bugs can actually be relatively easily converted to man-hour numbers. So this is a sort of an argument we can put forward when we discuss with our management our technology choices. So to be able to confirm that the investment in D is worth being done, we decided actually to make a proof of concept, some proof of concept work, which would consist of porting D to a target platform, evaluate dev tools and stuff like that. About porting, from experience, porting process is usually quite straightforward and I would say rarely gratifying. Matching platform-specific stuff on code on one side to the general purpose code on the other side, when most often none was written to be matched together, is actually pain in the butt. On the positive side, it can be used as a convenient entry point to gather the knowledge about the technology, new technology. When porting, you go under the hood very quickly, and you discover good and bad sides of the technology, which gives you a good overview where you are going actually. So in Ubisoft, we have a certain experience with porting. We work on several platforms at the same time, and porting to a new one is a usual activity. Me, myself, I ported code to about at least 10 different consoles platforms in the last 20 years. So I was confident that porting can be done, but I have never ported such a low-level software like compiler, runtime, and things we get for granted when you get the toolchain. So it was difficult to estimate the cost. So this presentation actually describes my efforts when porting D to this new platform, and hopefully will help other people plan for future porting efforts. So porting D, roughly we can split into 3 phases: choosing the compiler, porting D runtime, and porting Phobos. This is how my talk will be organized also. I'll explain how I have chosen a compiler for my platform. I'll describe the challenges when porting D runtime, especially the challenges to get built-in unit tests running, followed by the challenges when porting Phobos. I'll wrap up with the current status of the proof of concept and the results. So the compiler. The first decision to make when porting to the new platform is the compiler to use. In general case, this is not a question since your platform provider usually provides the official toolchain, which includes the C++ C compiler. But for D, depending on hardware, you can have more or less choices. The more exotic the hardware is, the less choices you will probably have. Your choice is you can also have a natural choice, sort of, in a sense that you can align your choice to the C++ compiler you get from your platform, like GCC, GDC, clang, LDC, and etc. So in my case, the choice was sort of obvious because platform is using clang, so LDC was a natural choice. Well, it's not straightforward, however, because platform modifications to LLVM are closed source, so I don't have access to it. But it's not a blocker, because I can start from the upstream LLVM and do the necessary modifications myself. So the first problem the problem I encountered when trying to compile the compiler is choose the platform triple. The triple from the platform toolchain is not known by the upstream LLVM. As I said, modifications are closed source. So I hesitated to choose a well-known one like Linux or Android, since I didn't know how many configuration settings like defines, etc. will be brought in by this choice, and which my platform would not support. After some experimentations, I settled down with unknown Haiku, which seems to me to bring the smallest suppositions on the target OS. The long-term solution, of course, is to add the correct triple for my platform in LLVM, and this will be probably done in the future once I better understand platform requirements and specificities of LLVM. So once this choice is made, compiling the compiler for me was trivial. I just followed instructions on the net, which are very good and precise enough. When it comes to testing the result, luckily you don't need the runtime and Phobos for that. You can use better C, switch with the simple C-like code to verify if the compiler works, if the code generated can be run on the target platform. So this is also the opportunity to validate the debugger, to see if the source debugging work, breakpoints work, watchpoint work, because this for us is very important. If we don't have a debugger, this is a blocker. And it all worked reasonably well. So just before continuing, for the reference, these are the versions I worked with. There is no special reason for using these versions, but those were the versions, the latest versions at the moment I started working. Okay, so I had some specific problems while compiling the compiler, which might or might not be present in the latest versions of LDC. So I was hit by a command line length problem when compiling Visual Studio. I didn't want to deal with this, so I moved the source code up the folder hierarchy. And also, it seems that LDC is not built using Visual Studio on the continuous integration servers, since there is a problem with link flags in a CMake file. So I made a fix locally, and I need to check if the problem still exists in the latest version and propose a patch for that. Compiling the compiler did not require big changes. Therefore, the question of development environment did not pop up. But before starting porting the runtime, I needed to set up and test the development environment. So as in Ubisoft, we work on Windows with Visual Studio, and the target platform toolchain is Windows, Visual Studio based. The choice to use Visual Studio as development environment was the obvious one. Luckily, we have Visual D, which works reasonably well. It's not on par with the C++ environment, but this can be worked on in the future, and the improvements are definitely possible. I also needed to add the support for the target platform in Visual D, and it actually turned out that it's not that complicated. The end result makes no modifications to Visual D. It's just additional property sheets which can be installed separately. I also decided to use C++ projects. This is something we are used to, and mix D files inside. This also corresponds to the expected final usage, so it makes sense for us. So with the compiler and the environment ready, the development environment ready, it was time to start porting the runtime. So yeah, it's great when the code you are porting has a good unit tests coverage. And it's even better when you can run those tests, which of course was not my case, because I was porting code which was used to run unit tests. So the first goal to reach was to get the unit test running, actually. And it showed out that this simple goal was not so simple, actually. The minimum needed to run unit tests is actually quite big. So first I tried what I call the brute force approach. My strategy was very simple, actually. Enable unit test flag on a file, get it compile and link, run, fix the crashes, and repeat. I used it many times in different porting efforts, but with such a low-level code and not with a barely tested compiler. So after passing a considerable time stubbing all complicated stuff, I got the thing compiling and linking. And I expected actually the thing to crash quickly, but not before reaching the main. So I could barely attach my debugger to find out that the executable actually crashes in dynamic loader linker code, and I had no clue why. I have no sources for that. So I needed to step back and change the strategy. So I decided to throw almost everything away I did until now and start from the beginning. This time I decided to have something compiling and running all the time. As the D runtime can be initialized from C++ code by calling RT init, I decided to take this approach and started with empty RT init, RT terminate, and add gradually the content from the original versions. I was quickly able to confirm that the extend C functions work, started to manually test the interfaces to platform SDK I have written. And I had working mutexes in no time. And as built-in unit tests still didn't work, I used custom written tests and debugger when needed to validate the code. To avoid porting garbage collector, I used GC stub to test first allocations. and as expected, cmalloc worked immediately. Yeah. So having simple C-style allocations working, the logical next step for me was to test allocations using new and classes. And as simple as it sounds, it brings a lot of dependencies, object, lifetime, type info, etc. And again, I stubbed complex stuff, got the rest compiling, and when tried to run the executable, surprise, surprise, I got dynamic linker loading crash again. But at least this time, I could compare the running and crashing versions to try to figure out what was happening. I spent considerable time searching for the problem, studying map files, symbols, relocations, learned a lot how loading and dynamic linking work. And finally figured out that dynamic linker was crashing when trying to patch vtables, which were placed by the compiler and linker to read-only data section. So yeah, okay, it's normal that it crashes when it tries to write to read-only memory pages, but why it was there? So it turned out actually the default relocation model for my fake triple, unknown haiku, was static model. And actually it should have been pick, so position independent. So after I patched the compiler to fix this, allocating using new worked, and I had simple D classes. Yes?
How many days would that cost you?
How many?
Days.
Whew.
Just this
maybe,
one.
let's say this one, maybe a week, something, probably. So once allocations using new were working, getting asserts and exceptions to work was easy. Need some fiddling, but nothing worth remembering actually. So having asserts and exceptions working, I was expecting that unit tests could work actually. The only remaining problem was to know which unit test exists. So unit tests actually are discovered automatically through the module info. So getting module info to work is a fine play between compiler, linker, and the runtime. So actually, module infos are generated by compiler and then passed to the D runtime. And LDCs already implement several strategies to pass the module info to D runtime. So it took me a while to understand all the possibilities and find the version which would work for my platform. And again, I needed to go back and configure my compiler specifically for my case. So I used ELF registry style and passed module info to the D runtime through init array. On the D runtime side, I ended up rolling my own implementation of sections for the platform, which is basically a stripped down version of ELF sections implementation which already exists, which was a bit too complicated for my case. And that made module infos working, and with working module infos, unit tests finally work. And once unit tests are working, everything becomes much more simple. Filling in missing parts becomes easy, adding file by file and making it compile and pass unit tests is relatively trivial. A few words about the platform-specific code. In the majority of cases, when trying to compile a file, the platform-specific code contains at least one static assert for unknown platform case. So this is the indication that the file needs your special attention, and once this file is identified, you will need to go through the whole file, line by line, to understand what needs to be done. Because there is often only one static assert per file, but many places to fill in with platform-specific code. To figure out what's the needed implementation, often you can get the inspiration from Windows or Posix implementations, which are there. It's also wise to grep version something keyword, because all platform-specific code is unfortunately not protected with static asserts, so you may miss some. One other subsystem deserved mentioning. It's a garbage collector. It has some tricky dependencies, threads, sections, virtual memory, which might get some time to get right. In my case, I decided to bypass virtual memory implementation problem for the moment. It's a well-known problem for us. We know how to implement that and has easy temporary solution. Use clib malloc free and it works. Threads are also mostly simple to port depending on the exposed platform SDK interface. It requires, however, some precision because there are many functions to fill in and the file is quite big. Finding your marks inside is not always easy, so you'll need to go slow. And to make GC work, your platform SDK thread interface must be able to actually suspend and resume threads. In my case, actually, this functionality was not exposed in the public headers. So for some time, I thought this is a blocker. Okay, I can't continue. But searching through the SDK library symbols, I found out actually that interface exists, but it's not exposed. So I simply exposed it in interface in D, and it works. So blocker removed. The other thing is that GC to work properly will need to know where are your BSS and TLS segments in memory. And this is something your section implementation, the same which implements module info in D runtime, must handle. Again, depending on the openness of your platform, you will encounter more or less problems with getting this right. Open platforms might give you the opportunity actually to browse segment infos because they are available to dynamic loader and linker. And of course, in my case, this is not available. So luckily for me, the linker exposes some necessary symbols. And by using some hidden C runtime functions like TLS get address, I managed to construct something which is working, but is not protected from breakage when updating the SDK. So another smallish issue worth mentioning that I encountered while wrapping Platform SDK C++ interface to D interface is C mangling problem. So while writing D wrappers, I very quickly encountered a strange link problem with some, but not all wrapped functions. During the link phase, functions were not found in the Platform SDK libraries, although they had correct signatures. So after investigations, it turned out actually that the C++ compiler is using substitutions for the namespaces when mangling. And it also turns out that DMD is not handling this correctly in a special case where the function or method is using extend C++ symbols for parameters, and those symbols are the same namespace but declared in the different file, so in different module. So this is not actually my platform or LDC specific problem because I managed to reproduce this in DMD on Linux. And the problem is actually, it seems known, but I did not manage to figure out if this is missing feature or it's a bug. In any case, for me, it's not a blocker because there are workarounds. And the one I'm using is a Pragma Mangle, which allows me to adjust mangling to match the C++ version. So it's not very pretty, but it works. So to recap, porting, D runtime was actually an interesting challenge. Having unit tests running was a major goal, which required a decent amount of work, investigation, and perseverance. Once this achieved, the rest became much easier. Standard porting work I was already used to. Also, getting sections implementation for GC working correctly was also a challenge, partly because of my lack of knowledge, partly because of the platform, which is pretty closed, and do not expose the interfaces similar to Windows or POSIX. So once the runtime compiling and all tests passing, I adapted the CMake build script to integrate my platform to the standard LDC D runtime, and that was it. So on to the next challenge, which was Phobos. So how hard can it be after runtime? It is higher level. It should be mostly platform independent, right? Well, not exactly as it turns out. So as it turns out, actually, 80-20 rule applies nice to Phobos porting. In terms of lines of code, 80% is either platform agnostic or can easily be ported. So has trivial dependencies like to ASCII D or something. And about 20% of code is platform specific. So there are no huge surprises in it, file, path, memory management for experimental allocator, socket system. So as expected. Also, 80-20 rule applies to time scale too, but inversed obviously. So 20% porting time is spent to get 80% of Phobos working, and the rest is spent to get the platform-specific parts ported and working. And speaking about platform-specific code, I actually divide it into two categories. The first one is being the code for the features which the platform supports. So in this case, porting will be trivial, fill in the gaps, check if the unit test passed, and that's it. The second one is more troublesome, and it's time-consuming, actually. There are features in Phobos which the target platform simply does not support. In my example, for example, process management is not supported, so these kind of features will not be ported and will remain unavailable. However, there are features which the target platform partially supports, so porting is possible, but not completely. So the choice to which extent the support will be implemented, none, partially, or fully, can depend on the porting cost versus planned usage, actually. In some cases, at least minimal implementation is needed because other parts of Phobos depends on it. So the ratio between those two categories will vary on the type of platform you're porting to. So here are some examples of the code which could be partially supported for my platform. One case is standard date time, which sounds unexpected and a bit surprising at first, but when you look at the time zone implementation differences between Windows and POSIX, you quickly understand that subject is not that trivial. Of course, my platform implements time zones completely differently, of course. Why not? But it's really relatively easy to adapt to the expected time zone interface, okay? But then you run the unit tests and you find out the surprising limitations. For example, my platform supports only dates between 2000 and 2100. Okay, so implementation is possible, but it's limited to a certain time span. In the expected usage case, this is acceptable, so it's not a problem. But there are a huge amount of unit tests which use dates outside the supported range. So either I need to find out the way to disable non-applicable tests or to adapt others to supported range, which becomes time-consuming and which brings back the question, will this really be used? So other choice could be drop support entirely, but this is not so easy because there are at least minimal implementation is needed because other parts of Phobos depends on it. So I ended up actually implementing it as much as possible with adapted unit tests, even though it required a lot of patience because the file is huge, 4,500 plus lines of code, and most of them unit tests which needed to be modified. The other example is file path and the get current directory. So as we know, get current directory function is declared in unistd header, which exists on my target platform. But when you look at the header, you find out that the function is unsupported. So few unit tests later, it's confirmed get current working directory, always return null. So my target platform does not support the notion current working directory, although it supports changing directories. As the executable actually starts with no available storage space, different storage spaces must be actually explicitly mounted before use. It's clear that the platform maker considers that the working directory does not have the same meaning as in general purpose OS, so it did not implement it. In any case, I must implement something because there are dependencies which require it. But is the full emulation or implementation on the D side is worth the cost comparing to the planned usage? Because in our code, we are mostly using full path to read and write files. So in the current iteration, I just hard-coded a certain path as a working directory, and we'll get back to this problem in the future. Two random problems actually I encountered while porting Phobos is some unit tests are crashing the compiler. I have no more details than that at the moment, but I need to investigate this in the future. It's interesting that I didn't have any compiler crashes when I was porting D runtime. And another interesting detail is that there is a small bit of code in numeric point D, which expects that malloc 0 returns a valid pointer. As it turns out, this is not true for all platforms, and actually standard says that malloc 0 is implementation defined. And of course, my platform returns null pointer and not valid one. That's how I found the problem. So yes, we learn every day something new. So to recap, Phobos porting challenges are actually hidden in platform-specific parts, which can be either partially supported or even not supported at all. So this is where tough choices are to be made, and most of the time is actually spent. This concludes the Phobos porting part, and I must admit I still haven't completely finished porting Phobos because 80-20 rules is there. But here are some conclusions. So the good news for us is that there are no blockers, technical blockers, but D works on the target platform. Dev tools on Windows and Visual Studio work, and they exist and they work. There is a room for their improvement, but they are not at the level of C++. But this is also the part where we can work with the community, and any work we do could be offered for the upstream integration. And I already done some for Visual D. So, which means that the proof of concept work continues, porting is still not finished, dev tools need work, and we still have a limited data on compilation speed. We will probably need some production code also to be able to estimate eventual gains. So this, what I presented, represents around 3 to 4 man-months work, taking into account that work was interrupted several times by higher priority tasks. And that brings us to questions. Yes?
You mentioned that deep in Phobos somewhere there's a call to a function that expects malloc 0 to return a unique pointer, and that's implementation defined behavior on malloc.
Yes.
So we'd like to get this fixed. Is there a Bugzilla entry for it or pull request to fix it?
Not yet.
Okay.
Not yet. I actually have in my code I do version this or that. But yes, probably the code should be rewritten differently.
Well, it's easy enough to fix. You just make it malloc of 1. Okay, and then you'll always get a unique pointer. But my larger point is all these porting difficulties that you have, please make a list of them, and then we can get them fixed so the next guy won't have to go through what you went through. So
Okay.
please do that. Just keep a log of all these issues that you run into with it. That would be most helpful.
No problem.
Yeah.
Stefan, yes.
I have a little question. If you can answer it, you didn't want to disclose the name of the platform. May I ask if the name of the platform vendor starts with S and ends with Y.
We can talk about that in private. I don't want to disclose anything. Sorry.
Is there any plans to contribute back your changes to upstream, runtime, Phobos?
Basically, no, because the code is under NDA. Most of the code is actually interfacing to our implementation, which calls the platform SDK. So what we do in Ubisoft is actually, if you are a game developer, you will have signed NDA with platform providers. So you can contact me, us, and we can share the code. I think there is no problem with that. But it will probably not finish in the upstream. There might be fixes or stuff like that, like what I did for CMake and also some other stuff. But yeah,
Well,
hard. It will be hard.
Will you fix the version of the compiler then? Because I assume you're going to have merge problems if you try to upgrade.
Yeah, I actually merged from 1.3 something to 1.4 at some point, and it was not that bad because I tried actually to keep the code sort of separated as much as I can, because I know that I will have merging problems. We live with that all the time. And yeah, but this is unfortunately the sad but true. We can't help that. The other possibility is, we could work actually independently of the implementation. We could eventually work on the runtime or the Phobos to make the interfaces much clearer, so that we can have platforms better integrated. Because today now it's like in C++, if def, it's like version, and it does not scale. With Windows POSIX, maybe it scales, but if we imagine that we have like games with 8 platforms simultaneously, so if we need to add 8 platforms here, so this will be, it does not scale. It won't scale, it will be ugly, let's say.
I basically have the same question, but then for LDC. And then perhaps you mentioned the platform uses Clang.
Yes.
Is that a private fork of Clang, or is it mainline Clang?
It's a private fork for sure, because there are platform triple already does not exist. So yes, they have a platform, and we asked for actually that they give us LLVM libraries in the SDK, but no response for now. So I need to go.
All right, so you'll have the same problems in upstreaming things to LDC.
Sorry?
So you'll have same NDA problems if you want to upstream things to LDC.
Yeah.
Right.
Yes. Probably yes. But there are other, because platform has, I haven't mentioned this there in the slides, but platform uses some stuff which is not implemented in LDC, and it's not working in the runtime and Phobos, which might be interesting to implement for other kinds of hardware of this type. We can talk about that privately, let's say. That there are pieces of hardware, with pieces of code which I put away because for us it's not really important, but we can improve we could work to improve the compiler support or the support in general for some kinds of operations which are processor specific, which this platform uses actually.
One question regarding the motivation. Do you have already decode you want to port, or is it just an evaluation if you could use deep code or use deep language in future games? Or
The motivation was from Remedy, let's say, because we followed D for a long time actually, but we never did anything because we thought, okay, platform providers won't agree, but actually as Remedy shipped some games with D inside, we said, oh, but this is actually possible. So we said, let's try and see how it goes. Do we have code? No, actually we don't have any. And we will probably, if this goes to some kind of positive conclusion, we will probably try to choose some subset of our engine or something to implement it in D, whether this will be a port or this will be a new feature. It remains to be decided, actually. We don't have clear plans, actually.
what's your personal conclusion so far? Is it possible, or is there any blocker?
As I said, it's clearly possible. We still don't have actually good compilation results, but it's a mixed. It's a mixed bag actually today. I'm not sure where the problems are, because when I compile D runtime, for example, with Ninja and command line, it compiles really fast. When I compile it with Visual Studio with Visual D, it's not that good. So we need to. I already have some plans, and we need to investigate in the tools now what happens with, because we won't compile with Ninja, this is almost certain. We do everything in Visual Studio, so we need to get this part working well. So we are ready to invest some time to figure out what are the problems and how can we make this better, like the multi-process compilation and different stuff, which actually does not work today. Yes.
Were there other languages considered?
No, because actually or other languages today people talk about, like Rust, Go, are actually too different to what we do today. D is actually like C, C++, that we want actually to have a easy conversion path. So we want to actually to profit from some stuff we wait in C++, which will be coming, but they are already D, and so we ask ourselves, why wait when it's already there? And now we are trying to see how costly it is to make this transition. Yes.
Yeah, one question also about considering the languages. Have you considered JAI at all?
JAI.
That's Jonathan Blow's language.
All right, then probably you didn't.
No.
Okay, so first of all, thanks for the great talk. And
Thank you.
there was two main motivations you named. There was one being able to compile faster, especially like you said, like your incremental builds take like 10 minutes or something.
Yeah, our current project, it's like 1 million lines of code, something like that. It compiles in full rebuild, it's like 15 minutes. But we have many different optimizations to compile this. Like we have a Incredibuild, so we launched the compilation on 50 machines, all in parallel, whatever. Because on one machine, it would be probably at least 1 hour.
Mm-hmm. And the other one was memory safety. So
Yes.
yesterday we heard about someone using BibeD and they had like memory leaks and stuff. And like, where does this motivation, like how do you like associate D with memory safety?
This is all what we heard from Walter's talks and stuff like that. What we want is actually to bring it at least, because we split our work in Ubisoft, our teams are basically split into two. Let's say that we have an engine team which works on lower level stuff, and we have gameplay team which works on sort of higher level stuff. And for us, already a win would be to put all gameplay programmers to work on some safe version of D. But of course, all what is garbage collector for us is not an option. So I ported garbage collector for completion to have a complete picture, but we do not plan to use it. So all the developments happening to be able to use language without garbage collector, we are very interested in that.
Thanks.
Yes.
You said that compilation time is important. Do you have any reason to believe that compiling with D will result in smaller compilation times? Or is it just a hunch?
We don't have that much experience actually. Last year actually, we came last year here, not here, but in Berlin on the DConf, and one morning, one of the mornings, I took the DMD and Phobos and all the stuff, and I said, okay, I'll launch the compilation, I will take a shower, and then I come back, it will be compiled, like LLVM, for example. And then I launched, it's finished. It's not good. I don't know, it works, okay? So this tells me that there is improvement is possible. I mean, it's fast. We don't have a code, the C++ code that compiles that fast. So if you say, okay, we have LLVM, we have DMD, LLVM compiles for, let's say, 1 hour, DMD compiles like 5 seconds. Okay, they are not the same size of code and everything, but there is a huge difference in the compilation time. So this is something we want to confirm, that this really is interesting for us. And we have, what we hear here is that there are people who have problems, all is not roses, when compiling D, but yeah. We need to see, and that's why I say we need more our code actually to see what we write, how this will behave in D. Because we don't have that complicated code actually.
Okay, any more questions? All right, thank you very much, Igor. That was a great talk.
Thank you.
All right, and it's lunchtime. So everybody go eat, and we'll see you back here at 2:28. Thank you.
Thank you.